Now there are three theorems here that I want to quickly talk about. A couple more. Suppose that F is a vector field that's continuous on an open connected path. Region. Now, if the line integral f dot dr is independent of path in its domain, then F is a conservative vector field on that domain. That's to say that there exists a function f such that this vector field is equal to the gradient of f. So we're saying here is that we're supposing that f is this continuous vector field on this open connected region. And we're going to say that if we know that it's path independent, then f is in fact a conservative vector field, and that this situation exists. It doesn't necessarily tell us how to find it. It simply tells us that this is true. Now, here's another theorem. If the vector field f equals the vector pqr, or p, q, and r are functions in 3 space, so p would be p of xyz, q of xyz, r of xyz, or simply pq, where p is a function of x and y, q is a function of x and y in 2 space, and f is a conservative vector field where p, q, and r have continuous first order partial derivatives on the appropriate domain, simply meaning whatever our domain is, whether we're dealing in 2 space or 3 space, then the following is going to be true. The partial of p with respect to y will be equal to the partial of q with respect to x. It's also true that the partial of p with respect to z will be equal to the partial of r with respect to x, and the partial of q with respect to z will be equal to the partial of r with respect to y. Now obviously this is in R3, and if we're only working in R2, we have the same idea, but it's much more compact. The partial of p with respect to x, with respect to y, will be equal to the partial of q with respect to x. Now, this is nice to know, it's useful, but where it kind of falls short is that this does not give us a means of actually determining if f is in fact a conservative vector field. This is a one-way implication. We need some stronger conditions to get a two-way implication out of this. And that's exactly what our next theorem is going to do for us. So here's the third theorem I want to talk about. Let's let f be a vector field in 2 or 3 space on an open, simply connected region. See, before I had open region, now I definitely said that it's simply connected. I added this component to right here. And again, either in 2 space or 3 space, if p, q, and r have continuous first order partial derivatives, obviously if I'm in 2 space, I'm only interested in p and q. I need the r if I'm going to be working in 3 spaces. And partial of p, this is actually the same thing I wrote a moment ago, with respect to y is equal to the partial of q with respect to x, and the partial of p with respect to z is equal to the partial of r with respect to x, and the partial of q with respect to z is equal to partial of r with respect to y. Again, this is in 3 space, or in 2 space, simply the partial of p with respect to y is equal to the partial of q with respect to x. Then if we can show that these partials are true, then I can say that f is a conservative vector field. Oops. See, the other one said basically if we had a conservative vector field, then we would find that these are true. But it did not allow us to go the other way because we need to add to this the idea of the region being simply connected. So once I know that my region is simply connected, now I can check to see if this is true by taking these partials. And if this is true, I can arrive at the conclusion that F is in fact a conservative vector field, which does all kinds of stuff for us in terms of trying to integrate over that particular vector field.